Hello, Matt here from chemistrystudent.com. In this video, we're going to look at bond enthalpies. We're going to talk about what bond enthalpies actually are, how mean or average bond enthalpies can be used to predict the enthalpy change for a particular reaction, why these predictions sometimes differ from experimental data, and how bond enthalpies can be used to explain activation energy. Enthalpy and enthalpy change have been covered in separate videos. Check the links in the description below. Before we talk in detail about bond enthalpies, there are a few essential ideas you need to be comfortable with. Atoms are held together in molecules and compounds by atomic bonds. The stronger the bonds holding the atoms together, the harder it is to separate them. Enthalpy is the heat content or thermal energy store of a substance or system. All molecules and substances have thermal energy stored up inside them, as when some of their stored energy is released, it can only flow out in the form of heat. Enthalpy change is defined as heat energy change, kilojoules per mole, measured at constant pressure. It is impossible to know the exact enthalpy of a substance. It is possible, however, to measure how the enthalpy of a substance changes when it reacts. This means in chemistry we work with enthalpy changes shown as delta H rather than total enthalpy values. Exothermic reactions describe reactions where energy is released overall by the reacting particles, making the products formed lower in energy and more stable, but increasing the heat content and temperature of the surroundings. These reactions have a negative enthalpy change as the amount of thermal energy stored up inside the products is less than in the reactants. Endothermic reactions are when energy is absorbed by reacting particles, making the products formed higher in energy and less stable, but decreasing the heat content and temperature of the surroundings. These reactions have a positive enthalpy change as the amount of thermal energy stored up inside the product is more than in the reactants. Recap done? Let's go! Atoms form atomic bonds based on electrostatic attraction. Whether it be the attraction of oppositely charged ions to each other in ionic bonding or the attraction of a shared pair of electrons to positively charged nuclei in covalent bonding, it is ultimately attraction forces that pull atoms and ions together and leads to bonds forming between them. Oppositely charged particles attract as when they are closer together their energy decreases. This means when covalent bonds form and shared negatively charged electrons get closer to another positively charged nucleus, energy is released and the bonding atoms become more stable. Their energies, or enthalpies we should say, decrease. An exothermic process. If a bond is broken, energy must be given back to each atom to enable it to overcome the forces of attraction that led to the bond forming in the first place. This means to break a bond between atoms, energy must be absorbed by the bonded atoms and their energy would increase as a result. An endothermic process. For example, a molecule of hydrogen forms from two hydrogen atoms, as the lone atoms are unstable and have a higher energy electron configuration than when they're bonded together. As they get close to each other and a bond forms between them, they become more stable and lower in energy. Their enthalpies decrease. The atoms release a little bit of energy as the bond forms. To break this same bond, the same amount of energy would have to be put back into the two bonded atoms to enable them to become the same as they were before the bond formed. This amount of energy is referred to as bond energy. Different types of bonds will naturally have different bond energies, meaning that breaking and forming of new bonds among molecules in a reaction leads to an overall change in energy as reactants turn into products. This is where the enthalpy change of a reaction comes from, the breaking and forming of different types of bond. We can't ever really work with one single bond in chemistry. In a reaction, even on a small scale, there are still billions of bonds being made and broken. meaning rather than try to find the energy change for one bond being made or broken, we refer to the enthalpy change that occurs when 1 mole's worth of a particular bond type are made or broken. These enthalpy changes are called bond enthalpies. A bond enthalpy is the enthalpy change that occurs when 1 mole's worth of a particular bond is broken in a gaseous phase. As we've already seen, bond breaking is an endothermic process. Energy is needed, and the enthalpy of the bonded atoms increase when a bond gets broken. This means bond breaking has a positive enthalpy change. Making bonds is an exothermic process. Energy is released by the bonding atoms, and their enthalpy decreases. This means bond making has a negative enthalpy change. I am repeating this as it's very important. The useful thing about bond enthalpies is that they can be used to find the enthalpy change for a reaction. In a reaction, reacting molecules react to form new products. This means bonds in the reactants have to be broken and new bonds then formed to make the products. By comparing the enthalpy change that occurs when the bonds are broken and the enthalpy change that occurs when new bonds are made, we can find the overall enthalpy change that must have occurred. Now, I should point out here that this is all theoretical. In reality, when a reaction happens, it isn't like all the bonds in the reactants get perfectly broken and then new bonds form. It kind of all happens at the same time in a big mess of electrons moving. We can simplify the reaction process down in this way though and use it as a really useful model to explain why and how enthalpy change occurs in a reaction. For example, in the combustion of propane, C3H8, all the carbon-carbon and carbon-hydrogen bonds in the propane molecule must be broken in order to react with oxygen. Molecules of oxygen reacting must also have their bonds broken to free up oxygen atoms to form new bonds with the carbon and hydrogen from the propane. By looking at the bond enthalpies for the bonds in the propane and oxygen, we can see the enthalpy change that occurs as these bonds get broken. In 1 molecule of propane, there are 2 carbon-carbon bonds and 8 carbon-hydrogen bonds. This means in 1 mole's worth of propane, there are 2 moles worth of carbon-carbon bonds that must be broken and 8 moles worth of carbon-hydrogen bonds that must be broken. Looking at the bond enthalpy data for these bonds, we can see that the carbon-carbon bonds have a bond enthalpy of 346 kilojoules per mole and carbon-hydrogen bonds 413 kilojoules per mole. There are also 5 moles of oxygen molecules reacting, meaning 5 moles worth of oxygen-oxygen bonds must be broken, with oxygen-oxygen bonds having a bond enthalpy of 497 kilojoules per mole. The enthalpy change that occurs when all the bonds in 1 mole's worth of propane get broken must be 2 times 346 from the carbon-carbon bonds and 8 times 413 from the carbon-hydrogen bonds. Also factor in the 5 moles worth of oxygen-oxygen bonds, 5 times 497, and this gives a total enthalpy change of 6,481 kilojoules per mole. Another way of looking at this is that 6,481 kilojoules of energy is needed to break all the bonds in the reactants. After these bonds have been broken, new bonds have to form. In the products, carbon dioxide and water, we have carbon-oxygen bonds and oxygen-hydrogen bonds. 3 moles of carbon dioxide molecules means 6 moles of carbon-oxygen bonds, and 4 moles worth of water molecules means 8 moles worth of oxygen-hydrogen bonds. Using the bond enthalpies shown, we can see that the total enthalpy change for forming all these bonds is 8,144 kilojoules. 6 times 740 for the carbon-oxygen bonds, and 8 times 463 for the oxygen-hydrogen bonds. We now know that for this reaction to occur, there is an enthalpy change of positive 6,481 kilojoules per mole to break the bonds in the reactants, and then an enthalpy change of minus 8,144 kilojoules per mole when all the bonds in the products are formed. Remember positive enthalpy change for breaking the bonds as it's an endothermic process, and negative enthalpy change for making the bonds as it's an exothermic process. There is a difference here of minus 1,663 kilojoules per mole. This would be the enthalpy change for the reaction overall. As it's a negative enthalpy change, that means the reaction is exothermic, and actually 1,663 kilojoules of energy is released overall in the reaction. If you're unsure about that last bit, please check out the video on enthalpy in the link given in the description below. To find this enthalpy change of the reaction, we can take the sum of bond enthalpies in the reactants and subtract the sum of bond enthalpies in the products. Sum of just means all added together, and we show this in a formula with the symbol uppercase sigma, a bit like a strange E. Having said that we can use bond enthalpies to find enthalpy changes for a reaction, there is one major problem. The bond energy for any particular bond is based on the energies and arrangements of the atoms involved in the bond. This means the bonding atoms for the same type of bond in two different molecules will have slightly different energies, and this will change the exact bond energy in their particular molecule, even though the bond types are the same in both molecules. For example, there is an OH bond in all alcohols, and yet the alcohols themselves can be completely different, meaning the OH bond in each will have ever so slightly different bond energies and require different amounts of energy to break. If the environments of two identical bond types are different in two molecules, they will have slightly different energies. It isn't realistic to know the exact bond energy for a bond in a specific compound, and this is why the bond enthalpies used in calculations are average or mean bond enthalpies. These values are found by taking a wide range of compounds with the same type of bonding and finding the average value for the bond energies, given databook bond enthalpies. The differences between the bond energies for bonds in different molecules will be very small, but still, the use of average bond enthalpies can mean the enthalpy change values calculated for a reaction using them is different to the actual experimental value you obtain in a laboratory. Modeling reactions in the way we have so far means that in order for any reaction to happen, bonds in the reactants have to break first. Without these bonds breaking, no new bonds can form and no new products can be made. As breaking bonds requires energy, remember bond breaking is endothermic, the start of a reaction needs an input of energy to break the necessary bonds in the reactants. This amount of energy is called activation energy and can be shown visually using reaction profile diagrams. The rise in energy between the reactants to the maximum energy the reactant system reaches is the activation energy. So, to summarize, energy is required to break a bond between atoms, and energy is released when a bond is made. For the same type of bond, this amount of energy will be the same and is referred to as bond energy. Bond enthalpy is the enthalpy change that occurs when 1 mole's worth of a particular bond is broken in gaseous phase. Bond breaking is endothermic, energy is required, and it has a positive enthalpy change. Bond making is exothermic, energy is released, and it has a negative enthalpy change. The overall enthalpy change for a reaction can be found using bond enthalpies. Delta H, enthalpy change, equals sum of bond enthalpies in reactants minus sum of bond enthalpies in products. Bond enthalpies are average values based on data from many molecules that contain the same type of bonds. This means the actual enthalpy change when a specific bond in a substance is broken may be different to the bond enthalpy data. Activation energy is the energy required to break the bonds in a reactant needed to start a reaction, and can be shown using energy profile diagrams for a reaction. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.